like I said, for lesson 3 here, periodic table. So we're going to talk about a little bit about the periodic table. Pretty general. In Chem 20, you'd get into a little bit more involved in that, but pretty general. And atomic structure. So what does an atom look like? And we're going to talk about protons, electrons, neutrons today, how many of each one, and whatnot. So you'll need your periodic tables out as well, right? Okay, so today our goal here is to, of course, explain using the periodic table how and why elements combine to form compounds. Write the standard atomic notation for an atom. So what does that look like if we were to write out a specific atom? And also draw Bohr Rutherford diagrams to illustrate the structure of an atom. Usually we just call them Bohr diagrams, and when we get to Chem 20. Okay, you're going to have a quiz. We'll have a quiz. Let's just do lesson 1 tomorrow. I think is okay. So we'll do lesson 1. Anything lesson 1 for tomorrow, like WMIS. Maybe some of the diagrams and things like that, okay? So probably not too many questions, but we need to know what those diagrams look like and be able to identify those, okay? And also, like I said, take a look through lesson 1 there and go through that, okay? Here's some review stuff. We're going to skip that for right now here because we just talked about that in the homework. Let's go to Bohr diagram here. Yeah, okay. Quantum mechanic model, there we go. Okay, so here we go. Periodic table and atomic structure. Elements are made up of only one type of atom, okay? Elements can be classified as metals, non-metals, or metalloids. And in your notes, guys, you'll have a picture of this, of course. Basically how it works is this is considered to be, well, this part here kind of thing, and up here like this. And you're going to see this staircase here. Actually, I think it goes down like that. And you can see it over there as well, the staircase. Those are considered to be, to the left of that is the metals, to the right is the non-metals. Okay, so the metals are over here, the non-metals are over here, and bordering those two, maybe I'm one over here. Yeah, I should have went like that, I guess. My bad. Actually, it probably cuts down like that. That's really bad. Anyway, the point is it's on your periodic table. The ones that straddle the staircase we call metalloids. They have properties of both metals and non-metals. Okay, so metalloids are a little bit of metal, they're a little bit of non-metal, and it really depends on what you react them with. Depends on what kind of how they behave more like. So in some cases, like for example, antimony, Sb. Okay, which is right beside Te. I mean, no, that's funny. Te. Sb, antimony, depends what you react it with. In some cases, it behaves more like a metal. In other cases, more like a non-metal. Okay, so it really depends on what you react that with. What do we remember from last year? Let's talk about this. When you combine, let's say we talk about combining these elements together here. What is a metal and a non-metal? What kind of compound does that form? Jacqueline? Ionic. Okay. So if we took something from here and something from over here, right? Metal, non-metal would be ionic, right? What if we took 2 non-metals? Okay, so we just talked about stuff over here. What are those called? Do you remember, Darby? Yes, molecular compounds. Okay, they behave very differently, guys, and you'll get into that a little bit more in Chem 20, maybe a little bit here, but mostly Chem 20, and we'll talk about the big differences. Do you remember what happens between a metal and a non-metal? How do they become those compounds? Do you remember? Metals tend to what? You guys remember this? No? How do metals and non-metals interact? No one? Metals tend to lose electrons. Does that make sense? And non-metals tend to take those electrons in, yes? So they work together. Non-metals and non-metals, molecular compounds tend to what? Do you remember that? So there's a give and take for ionic. Molecular is, yeah, they try to share. Okay, so they'll try to share electrons in that case. Okay, so that's what we're going to talk about today. Metals are on the left side, non-metals are on the right side. Metalloids are touching the staircase. That's Beyonce, I like to call her. Properties of metals and non-metals. Most metals are, and this is just for review, guys. If you looked at metals, they would be silver or gray in color, shiny, ductile, which means they basically can be pulled into a wire. Okay. Malleable means you can hammer on them. Okay, look, if you hammer on a metal, right, it might dent or whatever, but basically it's still intact. Okay, so they can be malleable. They're good conductors. Okay, and this is just for review, so I'm not going to ask you about this. This is actually something I'm going to ask you in Chem 20 rather. Non-metals vary in color. They're not shiny. They usually are dull. Okay, they're usually brittle. Okay, are poor conductors and are brittle. Metalloids have properties of both because, of course, they are kind of both. Okay, if you want examples of metals, just think about, a common one that we use in the lab all the time is aluminum foil. You guys have used aluminum foil at home, wrap up whatever food, right, and stuff like that, ribs. Right. Oh, here we go again. You wrap up stuff and food, right? And that's aluminum, guys. That's aluminum foil. We use it all the time for aluminum in the lab. That's what it looks like. It's shiny, it's bendable, it's malleable. I don't know how hard I'd hit it with a hammer, but it's ductile. Basically, you can work with it. Okay, they're good conductors. If you hook up a piece of aluminum to a battery, probably would conduct electricity. Absolutely. If you want an example of a non-metal, it's easy. Most of us probably have, well, at some point in time, used a pencil. Pencils are nonmetals. Carbons, a bunch of carbons linked together. They're dull. They're not particularly shiny. They're not like aluminum. They're brittle. You push too hard, it breaks. Okay, that would be an example of a nonmetal. All right. So that's just a little bit of review. This is important. We need to know that there's two ways that we arrange stuff in the periodic table. There's something called groups, which are the up and down vertical, okay? And we have names for these groups, but we'll probably worry about that later. Groups. So groups are group 1, group 2, we have groups 3 to 12, 13, 14, 15, 16, 17, and 18, okay? So those are the groups. We also have something called periods, and periods go horizontally, so that means this way, okay? And what we'll talk about is basically the periods are, there's nothing really, the atoms are arranged in the group for a reason, okay? Group 1, these all have one extra electron that the metals are trying to get rid of, okay? Group 2, they all have 2 electrons that the metals try to get rid of, okay? They're arranged in that group because they have similar properties. And those properties have to do with valence electrons, electrons in the outside, energy level, et cetera, okay? Periods, the only thing in common about a period is basically that as you go from left to right, it's very metallic here, less metallic, and then we get to very non-metallic, okay? And that's really all that's in charge there. Also, the other thing is the number of rings in the Bohr diagram will be the same. Because if they're in the same period, they have the same number of rings as you basically fill up those electrons. Okay? All right. Atomic theory. So atoms have a nucleus that contains protons, positively charged, and neutrons, which are neutral. Electrons occupy specific energy levels around the nucleus. The first energy level can have 2. The second can have 8. And the third one can have 8. Okay? For our purposes, guys, we are not going to go past there, okay? And in fact, even in Chem 20, we don't really go past there a whole lot. But listen, if you forget how many electrons there are, it's easy. Get your periodic tables out. Look, follow with me. How many electrons can go in the first one? Look, 1, 2 can go in the first energy level, okay? That's where that comes from. The reason is because in atoms, we need the same number of protons as the same number of electrons, yes? We want the atom to be neutral. So look, Hydrogen's got 1 proton, 1 electron, neutral. 1 positive, 1 negative. Helium's got 2 protons, it's got to have 2 electrons. That's why you can put 2 electrons in the first energy level. Okay? This one has, look, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. This we're not going to worry about. Okay? Okay? So 2, 8, 8. Wait a minute, 2, 8, 8. Where'd it go? All right. Atomic number. Okay, now pay attention here, guys, and like I said, make some notes if you need to. All atoms of the same element have the same number of protons. The number of protons is also known as the atomic number. So when you see this for scandium, go ahead, let's find scandium on your periodic table. Let's have some fun here. It's a treasure hunt for scandium. Okay. Number 21, this right here, means it's atomic number 21. That tells you it has 21 protons. Okay. So this would have 21 protons, P+. Okay. All right. The number of protons is also the atomic number. So that atomic number tells you how many positives, P positives you have. And these protons, of course, are in the nucleus. All right. That's atomic number. Number of electrons. In a neutral atom, and when we say neutral, that means it has no charge. Okay. Neutral atom. The number of negatively charged particles, have to equal the number of positively charged particles. So if I had 21 protons, I'd have 21 electrons in a neutral atom. Okay? Protons and electrons have to be the same. Got 21 positives, I need to have 21 negatives to balance that out. Okay? Good? Now, this means that a neutral atom, the number of electrons is equal to the atomic number as well, okay, in a neutral atom. Would an atom with a negative charge, here's a question for you, would an atom with a negative charge have more or less electrons? Think about that for 1 second. So, would an atom with a negative charge have more or, less electrons? More or less electrons. Negative charge. And what do you think? An atom with a negative charge, does it have more negatives or less negatives? It's simple math, guys. Look, if you have more negatives, you would have a negative charge, yes? Okay? So, Darby, more or less? More, absolutely. So let's say, I mean, it wouldn't happen with scandium because scandium's a metal. So it wouldn't happen with this, but, you know, if I said, hey, that's neutral again. Let's try this. You know, look at the difference, guys. Do math. It's simple, simple math. 21 positives. If I got 22 negatives, that's overall a -1, yes? So if it's got a negative charge, it would have a negative, it would have more electrons. This one, by the way, here, look, watch, guys. Notice, scandium can form a 3+ charge. It doesn't have to, but it can, okay? How do I get a 3+ charge? How many electrons would I have to have then? Yeah. Well, if I had 3 more, it'd be a negative charge. So 3 less, yes? So if I lost 3 electrons, does that make sense? Does that give you a 3+ charge? Okay, so that's what would happen with scandium. Scandium would lose 3 electrons, okay, to form that. But for right now, we'll just go back to neutral. So neutral, 21 protons, 21 electrons. Okay, that would be neutral. And metals tend to lose electrons. So it probably makes more sense to talk about scandium 3+, lose electrons. Okay, all right. All right, good. This one's got some writing on it here, so let me see if I can get rid of some of this stuff here. Yeah, just give me 1 second here. Oh yeah. Let's see. Mass number. Okay. So what is the mass number? The mass number of an atom is the total number of protons and neutrons. So it is the total mass of that atom. Okay, and we'll get into how they figure that out and whatnot maybe some other day. So let's go back to here for a second. Mass number. The mass number is right here, guys. Okay, this is your mass number. And this, once again, is the atomic number. Okay? So, mass numbers are a little confusing because you'll see it's 44.96. What we're going to do is we're going to round that up or down. Okay? So you're going to have to do a little rounding here. We're going to call that 45. Okay? All right? So we'll call this 45. What that means is this entire atom weighs 45 altogether. 21, remember, where does all the weight of the atom come from? The nucleus. The nucleus includes protons and neutrons. Okay? So protons and neutrons, look, I have 21 protons, but yet I have a weight of 45. And this was the issue they came up with. So they said, hey, if this is 21, how many more neutrons do I have to make the entire weight to 45? And the answer, of course, is 24. Yes? Okay? So I would need 24 neutrons for this one, because 24 and 21, 45 added together. Make sense? Or basically the mass minus the protons. So 45 is the mass minus the 21 protons gives me 24 jimmies. Ooh, tough crowd. Period 4, obviously. Awkward. That's as good as it gets, guys, so you might as well laugh now, because if you're looking for like a big zinger at the end, there's none. Okay? Just telling you. 24. Okay? So that's how you figure out the number of neutrons. Yeah. Okay? So, going back to here, if we were talking number of neutrons, right here, equals the mass number minus the atomic number. That's how you figure out the neutrons. The mass, the total big number, minus the number of the atomic number. Protons. How many neutrons would a carbon atom have with a mass and number of 13? So let's take a look at carbon. Find carbon for me. Look, find carbon. Okay. What does carbon look like? What's the atomic number of carbon? I gotta pick on somebody here. Yeah, Jeffrey. 6. No, that's not. You're not. Yeah, you're Jeffrey. Yeah. Jeff or Jeffrey? You gotta tell me. Oh. All right. What's the atomic mass of carbon? Usually on the periodic table, it's what? Asher? 12.01. We'd say 12, yes? We'd round it to 12. This one, though, says, look, the mass number isn't 12, it's 13. Okay? So this is what's called an isotope. We talked about that at the beginning before we started over. Okay, we'll come back to that eventually. So this one, okay, how many protons does this carbon have? How many protons does this carbon have? Let's see, I'm going to pick on someone. Melanie. Yeah, you. How many protons? Yep, 6 protons. How many electrons does this carbon have? Okay. How many electrons? What do you think? Sure. No. How many electrons? Yeah, Darby. 6. So we're doing a neutral atom, guys. 6 protons, 6 electrons, right? 0. Now, how many neutrons does this one have? How many neutrons? Huh? 7, right? Okay? These two added together have to give you the mass, protons and neutrons. Okay, so make sure you know protons, neutrons are the ones in the nucleus. Protons and electrons should equal each other in a neutral atom. Okay, good? Okay, that's important. Okay, isotopes. That last one we did is called an isotope, the carbon one. Isotopes are atoms of the same element that have a different mass. They have a different mass because they have a different number of neutrons. When you're walking down the street, okay, walking down the street, and you see carbon atom, you're like, hey, look, it's a carbon atom. Come on, guys. This is as good as it's going to get. You can't see a carbon. That's why it's funny, okay? You can't see one carbon atom. You're walking down the street, and you say, hey, carbon atom. Most carbon atoms have 6 protons, 6 electrons, and 6 neutrons. And I know that because on here, if you take 12.01 and round it down to 12, that's the most common isotope. So you have a really good chance of finding that one. Okay? Walking down the street, hey, look, 6 protons, 6 neutrons, there's my carbon. Occasionally, on the way to 7-Eleven, you're like, well, 7-Eleven, hey, oh, look, carbon atom. You'll see this one, the one we just did. 6 protons, 7 neutrons. Okay? That's not as common. You probably should buy a lottery ticket on the way to 7-Eleven when you get there. Because if you find that one, it's not as common, you might have a good chance of winning. Which then I was informed that you guys can't buy lottery tickets because you're not 18. Which I did not know. But I guess that makes sense. I don't know why, I just didn't think of that. So there is some of those 7 neutrons, and there's even carbon that has a weight of 14 as well. So some have a little bit more weight as well. Okay, the majority of them have a weight of 12. Those are called isotopes. Here's 3 isotopes of hydrogen. This is called 1 proton, so it's only got 1 proton. Some hydrogens are called deuterium, which have a proton and a neutron. And some are tritium, which is 1 proton and 2 neutrons. And that's just how they naturally occur, guys. Okay? The most common isotope is this one. The most common isotope of hydrogen has no neutrons. And I know that because if you look on your periodic table, there's 1 proton and the weight is 1. So the entire weight of that hydrogen comes from the 1 proton. Okay? That's how you know the most common one. It's the one on the periodic table. Hydrogen has a 1 proton, and it's got a weight of 1. That's the most common. Okay? All right? So those are isotopes. All right. Let's see here. So let's take a look at a few of these. Here we go. Mass number. And then you got your chemical symbol there, and atomic number. Okay? Quite often you will see this is how they are represented. So this is your standard atomic notation. So when you see that down here, for example, you should know what each one of those numbers are. The bigger the number, like the biggest number, has to be the weight. Okay? The smaller number has to be the atomic number. Now I'll tell you right now, you really don't even need to put the 6 there, do you? Because what do you know about all carbons? All carbon atoms have to have how many protons? 6. That's what makes carbon carbon. Okay? As soon as you move to 7 protons, now you have nitrogen. Okay? Every carbon atom will have 6 protons. That's guaranteed. In a neutral atom, we'd also have 6 electrons. What can change in an atom is the number of neutrons, though, and that is called an isotope. So, in this case here, guys, let's get you to fill this in real quick. Let's take a break here. Go ahead. I want you to tell me how many neutrons does each of the following have. You might as well tell me how many protons, electrons, neutrons each one of these has. Go ahead, do that real quick. All right, so, like I said, different number of neutrons there. Both have 6 protons. That's what makes carbon carbon. We can't change that. We never change that. Protons are protons. But what can vary is the number of neutrons. And once again, that's just how they naturally occur. The most common type of carbon is carbon 12 because it's 12.01 on the periodic table. If you round that to 12, it's 12. Okay? So, all right. Atomic mass. This is mass of one atom. It is the decimal number based on an average mass of all the possible isotopes. It is different than the mass number. So, what they're saying here is this, basically. This is the average mass of all the different isotopes, okay? To calculate that, it's a little bit, I don't want to say confusing, but you might say, well, Mr. Bachek, we talked about this. This is 21 protons, and we have 21 electrons, but then you told me that we had 24 neutrons, but look, that's 44.96. So what do you, like, what's going on? Because if you think about it, okay, we can only have there's no such thing, guys, as 23.96 neutrons, okay? Yes? You can't have 0.96 of a neutron. The neutron is the smallest subatomic particle. They come in holes. What they've done to calculate that, and I'm not going to spend a lot of time on this because we'll talk about it again in Chem 20, but what they've done is they averaged all the isotopes. So scandium comes in a weight of 45. It probably comes in a weight of 44. They've averaged all those based on the abundance of each one. So remember when we talked about earlier, you're walking down the street, you're most likely to find the carbon 12 one. That's because probably most of them look like that. That's the most common one. But they also averaged in the carbon 13 and carbon 14 ones as well. Okay, but not as much, so they've taken into account the percentages of those. That's where that number comes from. Okay, it's based on an average mass of all the possible isotopes for that element. Okay, and that's where that number comes from. So on average, we'd expect scandium to weigh 44.96 on average. Not one of them do that. There's none that weigh 44.96 exactly. Some weigh 44, some weigh 45, whatever. But if you average all those together and the abundance, then you get this number here. Okay, and that's basically what they're saying. All right. Let's see here. Well, I think we did this already, but let's do it again here real quick. That's fine. Okay. Look, it says here, how many protons and neutrons does chlorine with a number of 37 have? And its atomic number and the chemical notation for chlorine. So these are questions you're going to see today, guys. How many protons, neutrons does chlorine with a mass number of 37 have? Maybe you'll want to start with the chemical notation for chlorine. Well, chlorine would look like this. And if we're going to do an atom representation of this or a chemical representation of this notation, we'd put the mass up here. It's got a mass of 37. And we know, guys, if you look on the periodic table, all chlorines have a weight of 17, yes? So we know that this is going to be a 17 down here, okay? And if you want to figure out protons, neutrons, electrons, 17 protons, 17 electrons. And in this case, because it's got a weight of 37, I'd have to say, well, that'd have to be what? 20 neutrons. And of course, I get that from 37 is the mass minus the atomic number, or the number of protons, which would be 20 neutrons. So mass minus atomic number, basically, is what you're doing there. Mass minus the atomic number. Okay? Yep. Okay, good. Yes? All right. So that's how you're going to figure those out, right? All right. So let's see. Oh, okay. Bohr-Rutherford diagrams. Now, this comes back to protons, electrons, neutrons still. So we still need to use those, exactly what we did. The number of protons and neutrons, of course, are the nucleus. The electrons go in the energy levels around. And you got to remember, it goes 2, 8, 8, okay? And that's how it works. So I'll show you, probably the best diagram is kind of something like this here, okay? Now, here's an example of fluorine, and this is how I would draw it. This is a nice diagram and all this, but look, and feel free to write this down as well, guys, but I usually put the symbol in the middle. I put the number of protons and neutrons in the nucleus. Now, fluorine looks like this, guys. If you look on your periodic table, fluorine is number 9, yes? And it's got a weight of, help me out, 19.01, I think. Is that right? Oh, 19 exactly. 19, okay. 19.00, right? So we know it's got 9 protons. Those protons need to go in the nucleus. So I'm going to put those right here. 9 protons right beside my little symbol here. 9 protons, 9 P positives. It's got a weight of 19. So remember, and if you want, you can do it this way too, right? 19 minus 9 is 10 neutrons. So this has to have 10 neutrons. That is my nucleus, okay? That's the middle of the atom. That's where all the weight comes from. Then we're going to move to the electrons. I have 9 positives. I need to have the equal number of negatives, 9 negatives. So I can go in the first energy level. Bohr said in the first energy level I can have 2 electrons. So I'm going to put those in there. They've done this. 1, 2. Okay? I will accept that. That is fine. Totally fine. If you want to do that, if you want to split them up like that, that's fine. I personally usually put them together, but it doesn't matter. Okay? I'll be happy with either. I put them together. I'm just going to give you a different option here. Oh, sorry, that's not that's the nucleus there. First energy level. Okay, 2, and we're going to use dots to represent electrons. In the second energy level, how many can you have? What's the maximum number? 8. Do we need 8 in this one? How many more electrons do I need to put in there to get my total of basically 9, right? Because 9 positives, 9 negatives. I already used 2, so, Britton, how many more? Already used 2. I need another how many to get to 9? 7. Who said 7? Okay. I didn't think that was you. Okay. Okay. 7. So we need another 7. We don't need to put all 8 in. We just need 7 more. This is how they get filled up. So pay attention, guys. This will help you next year. Okay, so watch. Technically, they take positions as far apart as possible. 1, 2, 3, 4. Okay. Then they start to double up. Okay. So now I'd go back up to here. 5, 6, 7 more. Okay. 2 in the first, 7 more. That's a total of 9 negatives, which of course go with my 9 positives. So you might want to write that down. You'll see the same thing here, right? 2 are kind of together, 2 are kind of together, 2 are kind of, and then you got 1 by itself. Okay? Yep. Yep. Good? Yes? Okay? Okay. Let's try this one. You try it. Magnesium. 12 and 24. All right, so let's take a look at, on your periodic table, you'd see this 12 and 24.401. We'd round it to 24. That's the one we're talking about here. You may want to consider, well, let's figure out how many protons, electrons, neutrons there are first before we start doing any circle stuff here. So we'd say, okay, well, it's atomic number 12, so 12 protons. It's neutral. There's no charge on this, so it's 12 electrons. And 24 minus 12 is 12 neutrons. So, and they're not always like that, of course. They're not always the same number. We need to put the protons and neutrons in the nucleus, though, and then the electrons on the outside. So I like to put the symbol here, Mg. Okay. and I usually put 12 protons, 12 neutrons, and I start there. And that is the nucleus. Okay. Then I make another ring. That'll be the first energy level. Okay. I need to get a total of 12 electrons. Okay. And only 2 fit in the first one, yes? If you want to put them separately, fine. I'm not going to fight you. Go right ahead. Okay. That's fine. If you want to put them together, that's fine too. Okay. Those take up the first energy level. Then, in the second energy level, I can have 8, right? As much as 8 if I need to. Do I need 8 in that second one? Yeah, because I need to get all the way up to 12, right? So there's 2. Another 8 is only going to get me to 10. Yes? So I need to do 8. This is how they get filled up. 1, 2. This is now this. I'm not going to buck too much on this because, or I'm not going to. You know, you should do them like this because this is technically how it works, and it's going to help you. Trust me, I promise you. Okay, 1, 2, 3, 4. Then they start to double up. 5, 6, 7, 8. Okay, so that's a total of 10 now. Yes, and now we need another 2. Correct? That was 10. Now another 2. Now, the 2, okay, just so you know, I would once again probably start up here, 1. If you want to put it down here, that's fine. I usually just go in order again here. So 1, and I put the other one there, 2. Oh. Okay, 1, 2. All right. Formation of ions. So to get to ionic compounds, we need to form what we call ions. Ions are atoms that gain or lose electrons, so they can do either. Metals tend to lose, nonmetals tend to gain. Okay? And a charged atom is called an ion. When an atom loses an electron, when we lose electrons, it forms positive ions called cations. Make sure you know this. Make sure you know this. Okay? If I lose electrons, I have more positives than negatives. So more positives leads to like things like Mg2+, Sc, scandium 3+. Okay? When an atom gains an electron, negatively charged ion is called an anion is formed. Okay? I know what you're thinking. If this is a cation, shouldn't that be a dog ion? Because that's the opposite of cats. No? Okay. Oh, did I? It was still, I recycle a lot of stuff, guys. I'm probably going to stick with that. So it's still funny though, right? Yeah, no, it's funny, trust me. It's hilarious. The point is, well, I forget what I say a lot of times because I'm old, so it happens. So cation, anion, yes? And the charge of the ion is indicated with what we call a superscript. So what you'll see is not that really. You'll see Mg2+, okay? Or something like, for example, O2-. Okay, that's the charges there. So we use what we call a superscript. We put them up above. Okay? Good? Okay. All this is very important, guys, so make sure you know. Okay, that stuff there. I don't know what that means. All right. Draw the Bohr-Rutherford diagram for sodium 1+. For sodium 1+. And don't tell me nah. Not going to do it. Okay. Na1+. How would that change? How would that change? So draw that for me. Na1+. All right. Once again, you may want to consider before you get going here, you might want to consider, finding out how many protons, electrons, neutrons you have. So, I have, of course, 11 protons. Okay. How does Na1+, what does the 1+ mean exactly? What does that mean? how would I get a 1, oops, how would I get a 1 plus charge? Yep, there. Yeah, but how do I get this 1 plus charge? If I have 11 positives, how many electrons do I actually have here then? Anyone? Put your hand up. How many electrons? 10, okay? Because look, guys, 11 protons, usually we have 11 electrons. That's neutral, right? But look, if I have a 1 plus charge, that means I have to have 1 positive left over. If there's 11 protons, I need to have only 10 electrons, right? 11 positives, 10 negatives. Get a calculator. 11 positive, 10 negative. Overall is a 1 plus, yes? And the weight here, of course, is what? Really, it's 23. 23 minus 11 is 12 neutrons. Okay? So that now should help us draw this diagram. Protons and neutrons go in the middle with Na, 11 protons, 12 neutrons. By the way, if I'm going to do this one, I probably shouldn't just put Na, because if I just put Na, people would say, that's not Na, sodium, okay? Because I don't have the right number of electrons, is what they'd say. So we probably should put Na1 plus in the nucleus. So we know that it's the sodium ion, okay? Nucleus, first energy level. 2 can go in the first energy level. Second energy level. I could put 8 if I wanted to in the second energy level. Do I need to put 8? Yeah, because I already have 2. 8 more is 10, yes? And apparently that's what I need to use. So they actually, once again, 1, 2, 3, 4, 5, 6, 7, 8. Okay? This sodium has lost an electron, and that's what gives it its positive charge. Metals tend to lose electrons because at a positive charge, those electrons usually go to a non-metal. The reason this happens is because, if you remember, all elements would like to become like the noble gases. Okay? So they don't have to, but if they have the opportunity, they will try to either gain or lose electrons. Metals tend to want to lose electrons because they only have, like, sodium only has that 1 extra electron to get rid of, so it's pretty easy for it to lose it. Okay? So sodium tries to lose an electron, and it tries to become more like neon. Okay? And that's how it becomes more stable, if you want. Okay? Good? Yes? All right, so you guys got some homework there to finish off, I believe.